Okay, take two. Again, my apologies. A little bit calmer now. All right, so I wanted to keep the notes because you probably wrote them down. And so I'll just do a recap of what we were able to write, and then we'll keep going. So we can visualize sets using Venn diagrams, and they're going to be really useful just to, because sometimes it's hard to think about sets just kind of abstractly. And so if we can visualize them, then that's going to be really useful most of the time. And so what we do is we draw a rectangle, okay, and the rectangle denotes the sample space, so all possible outcomes. And so I have here the interior of the rectangle represents the sample space, and I am going to try to put a little tail on the C here for the sample space, because sometimes we're just going to use a plain capital C to denote set C, and that's going to be different. So just to try to keep them straight, I'm going to use this kind of C with a little bit of a tail on it. So for example, if we want to talk about the set A, A is a set in the sample space, and of course it's just a subset, and so we denote it typically using a circle inside the rectangle. Okay. So that's kind of the most basic thing that we can visualize here. And so we're going to use Venn diagrams to illustrate some of these basic terms that we need to have a good handle on. So the complement of an event A is basically the opposite of A, right? And so it's the set of elements in the sample space that are not in A, right? And so it's the kind of not A, or the opposite of A. In terms of notation, right, you may or may not be familiar with A and then a superscript C for the complement, okay? And in terms of set notation, right, it's all the X's, where X is some arbitrary element, all the X's that are contained in the sample space, right? So X is an element, that's this portion here, X is an element in the sample space. And then you're going to read this colon as such that, or at least I do, such that X, so X again is that element that we're talking about, so some arbitrary element is not an element of A, right? So it has to be in the sample space, of course, but it can't be an A, and that makes it the complement. In terms of visualizing it, right, if we've got our, oh, sorry, it made a, I don't know, it does the adjustment on its own. I don't know. The rectangle is the sample space, right? And so the complement of A is all this pink here, and it's everything outside of A. Okay. Next thing we want to talk about is the empty set, and I actually forgot to highlight it, so I'm going to do that now. The empty set is the event with no elements, right? Or it's a set, right? The empty set is a set. That's good. So it's a set with no elements, and it's denoted by kind of a null situation here. So it's an O with a dash through it, okay? Or a slash through it, I think it would be. And so what we mean by the empty set then is it's the set with nothing in it, okay? And so I talked about, okay, well, if you have the set with 0, even though 0 means nothing, right? 0, the number 0 is something, right? And so 0 is not empty. Okay, so that can be confusing, and that's typically one of those questions that we like to ask, right, to emphasize do you know that the empty set has no elements, right? 0 is an element, right? It's worth nothing, right? But that's not the point, right? It is an element. So the set with 0 is not an empty set, since 0 is in the set, right? And it is an element. Some things that we tend to rely on in terms of proofs, right? If we're trying to prove something, then sometimes it's useful to remember that the complement of the sample space, right, is the empty set. So the sample space is all possible outcomes, and then the opposite of that is no outcomes, right? So the empty set. Similarly, if you flip it, then the empty set, the complement of the empty set, so no elements, is going to be all elements, all possible elements, which is the sample space, right? And so these we use sometimes for proofs specifically. We talked about A as a subset of the sample space, right? But A could, if A is some set, right, arbitrary set, then A can also be a subset of a smaller set, B, right? Smaller than the sample space, not smaller than A. That can't happen. That's like trying to put a bigger circle into a smaller circle. That can't happen, right? And so A is a subset of B if each element of A is also an element of B, right? So A has to be smaller than B, right, is what that says, which I might add here. So A must be smaller than B. Okay. How we denote it is with this kind of lopsided C, or kind of, I didn't do a great job drawing it here. And it's hard, it's kind of like that, okay? And so we denote it by saying A is a subset of B, is how we should typically read it, okay? But for me, how I read it, because it's a little C, right, is I just read it as A is contained in B. And for me, that helps me just kind of understand that, okay, A is inside B, so A is a subset of B. So technically we should be saying A is a subset of B, but if you want to, because I find that it's helpful, you can say A is contained in B, and that's fine. Okay. So what it would look like, right, is, okay, B is a subset of the sample space, of course, and then A is a subset of B. We can extend that and say that if A is a subset of B, right, so if A is contained in B and B is also contained in A, what does that mean, right? It means that A fits inside B, right, but also that B fits inside A, right? And so you've got this equal situation, right? And so if that's true, then the two sets have the same elements. So what we can write is that A is equal to B. There are going to be cases where we need to prove that A equals B. And so this is how we would do that, right? We would show that A is a subset of B, right? And then vice versa, we would show that B is also a subset of A, and therefore A is equal to B. Okay. All right, good. So for these next two few definitions, okay, we're gonna let A and B be events, okay, or sets if you want to. Yeah, events, events are referring to the experiment, right? Where we run an experiment, so we do something that yields a random result, right? And so events or sets, we can use them kind of interchangeably in this case. So the union, I've highlighted that here because we're going to need to remember that term. So the union of A and B is the set of all events in A or B. Okay. It's also taking into account the events that are in both A and B. Okay. And I'll highlight that, or in both A and B. Sometimes people are confused by that last part, right? That it can be in both. Okay? But it can be, and that's the definition that we're using. So how we denote it is we have A and then a capital U for union, and then B. So A union B is how we should technically read it. Sometimes what I will read it as is just or, right? That's because I find it helpful to have that or, right? A or B, okay? If you're given a choice of, well, I was gonna say if you're given a choice between like chicken or fish, you know, when we used to fly, chicken or fish, but you'd end up choosing one, right? But you have the choice. You could have chosen either or, but where my example falls apart is you would probably not ask for both, but you could, right? And so bad example, I guess, but that's okay. So visually, what does this look like? So A or B, or A union B, the shaded area here is the union, okay? And so it's everything in A, so everything in the A circle or in the B circle, right? And so now we've covered all the A and B area, right? Including this overlap. The intersection of A and B is the set of all elements that are in both A and B, right? So when we're looking at the intersection, right, that's the overlap. Guess it's hard to see. Right, so the intersection is the overlap, and I read it as and, right? So it has to be in A and B. And I use those words just because it helps me remember, okay, for this, if I have an intersection, then it needs to be in both, right? So if it has to be in A, well, that's in this big circle here, the A circle, but it also has to be in the B circle at the same time. So the only area where that happens is this midsection, right? The shared overlap. Okay. If A and B are disjoint, then the intersection of A and B, right? So A and B has to be what, right? If we know that they're disjoint, right? And I'm kind of rephrasing it here, but disjoint, remember from probably Stat 230, is when you have no outcomes in common, right? And so they're disjoint if you have no outcomes in common. And so that means that the intersection doesn't exist, right? There are no elements that are in common. So it means that A and B is the empty set, right? No elements. So we can say A and B are disjoint if that's true, right? But it goes the other way as well, right? This is kind of a two-way street, right? That's not always the case though. So, but in this case, right, if they're disjoint, then A and B is the empty set. And if A and B is the empty set, then they are disjoint. Okay. Visually, disjoint sets look like this, right? No common overlap. If A and B are disjoint, right, then the union of A and B, right, so A or B is called a disjoint union, right? And so, and I drew it kind of here. It looks like a little cartoon, and he looks sad. But really what I meant for it to be was a disjoint union between A and B, but that's okay. I'll leave it there. Actually, I should probably erase that, because if someone's just looking at the notes and not the video, it'll make no sense, right? And so if they're disjoint, right, and we want to look at the union, so A or B, then it's going to be those two circles. Okay. So then we had a little example where we said, suppose we have a spinner. So imagine, you've got a spinner with numbers 1 through 10, okay, on it. It's assumed that it's discrete values, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And so that's assumed, okay? But the experiment is to spin the spinner and record the number spun. I'll clean that up so it's easier to read. Spun. Okay. So you spin the spinner one time, that's running the experiment one time, right? And then you land on a 4, okay, and then you record a 4. So in terms of our sample space, the sample space are positive integers up to and including 10, right? And so I want you to try to practice if you can summarize a set verbally, that's good, right? So this, these are positive integers up to and including 10. Okay. That would also describe the set. Usually we just use set notation like this. 1, 2, 3. You could even trail off at 2 if you wanted to, but and then up to 10. So what we're going to do is we're going to let A be the set of either 1 or 2, right? And so if you spin a 1 or a 2, then we say that event A has happened, right? For B to have happened, we need a 2, 3, or a 4. And for C to have happened, we need a 3, 4, a 5, or a 6, right? And so C is the biggest set, I would say. Well, I would say that's a fact out of these 3, right? Because there are 4 elements. Let's see here. This is where we pick up. Okay, good. So this is where we start sort of fresh without a barking dog. He calmed down, but took some time. Okay, so get my keyboard out of here. Don't need that, don't need this. All right. Hey, I forgot to move my microphone closer. ASMR. I don't think it's that good of a microphone, but what I want us to do, is find the complement of A, right? So if we know the sample space and we know A is 1 or 2, then we can easily find the complement of A, and it is what? It's going to be not 1 or 2, but it's all the other values, right? So 3, 4, 5, 6, 7, 8, 9, 10. You could have shorthanded that somehow with some ellipses here, but I got carried away. So there's no harm in that, in writing out all the values, especially if they're so few like this. So the next thing I want to find is A union B, right? So A or B, right? Because when I say union, it's hard for me to think what I should be doing, right? But when I say A or B, then I'm just listing all the values that are in either A or B. Okay. And so if I look at A, well, I have 1, 2, and then 2 again. I only need to list it once though, and I should only list it once. So 1, 2, 3, 4 is going to be A or B. 1, 2, 3, 4. Only list each value once. Excuse me, we'll sneeze. What about A and B, or the intersection of A and B? Okay, so now, and we already kind of mentioned it, right? Now, only values that are in both A and B are going to be in the set. Well, that's just the set of 2, right? The only overlap here is the 2. What about A and C? Notice that this is not a script C, it's just referring to this C. Okay. And that's where it can get a little bit confusing, right? But I'm going to try to put a little tail on the sample space if it is. And so here, maybe I should say like that. A little tail on the sample space. Try to. Okay, so A and C, 1, 2. Is there any overlap with 3, 4, 5, 6? No, there isn't, right? And so the set of A and C is the empty set. That's okay. That can happen. In fact, it happens a lot, right? So that's okay. How about B and C? Looking at all the possible combinations here. B and C. So now I want overlap between B and C here. And there are no 2s in C, but I see 3 and 4 are in both sets, and then 5 and 6 is only in C. So B and C is 3, 4. Notice that B and C is a subset of B, right? Because 3, 4 is a subset of 2, 3, 4, but B and C is also a subset of C, 3, 4, 5, 6. Right? So that's just a little side note here. Notice that B and C is contained in B, and B and C is contained in C. Uh-oh, context makes all the difference here. So B and C is contained in C. In fact, maybe I should try to make it a little bit more square or kind of squished, I guess. Let's kick it up a notch. Okay, so let's find A or B and C in brackets. I think I'm going to break this down a little bit, right? And say that, okay, well, I know what B and C are, right? But it might be easier to just look at them as sets. So A, just as a refresher, is 1 and 2, right? And so what I have, A is 1, 2. Or B and C is the set 3, 4. Yeah. If we didn't have 3, 4, so if we didn't have B and C worked out already, these brackets say that we should deal with that first. So we need to figure out what that is first, and then we can plug it in. Find this first. Okay. So if we're interested in 1, 2, or 3, 4, the set that we end up with is going to be 1, 2, 3, 4, because it can be in any one of those values. How about even harder? What if we have to find A or B? And A or C. We have, where is it? We have A or B already, right? That's 1, 2, 3, 4. Okay, so what I'm going to do is I'm going to say 1, 2, 3, 4. And A or C. Looks like we don't have A or C, so we're going to have to find it. So A or C is 1, 2, 3, 4, 5, 6. Then we're interested in the and, right? The intersection. So the intersection of 1, 2, 3, 4 and 1, 2, 3, 4, 5, 6 is going to be 1, 2, 3, 4. Sorry, let me just go blow my nose. Maybe I'm allergic. Yikes. Okay, sorry about that. All right. So notice that we ended up with the same set. That's not a coincidence, but we'll do one more example before we talk about that. Okay. All right. In fact, here it comes. Usually we're not talking about just discrete values, right? So not just integers. Often we're going to be talking about numbers on a number line, right? And so, for example, suppose the experiment is to select a real number. A real number? No, thanks. A real number is any number, right? So remember, the set of reals is denoted by a capital R with like a thick back, right? And so is the set of real numbers, and it's the set from negative infinity to positive infinity and every value in between. Now, if you want to think about something kind of mind-blowing, right? Even between 0 and 1, we could get to infinite number of values between 0 and 1, depending on how deep we go, right? And so even just in that short distance between 0 and 1, there are an infinite number of values. And so from negative infinity to positive infinity, it's just really hard to wrap your head around how many values that are, but it's, or how many values that is, I guess. But it's just any value that you can think of, right, is in the set of real numbers. So the experiment is to select a real number, okay, in the open interval 0 to 5. Okay. This is as opposed to the closed interval. The closed interval would be something like maybe 0 to 5. And you can have a half-half interval, right? But in this case, we're talking about the open interval, which means we're going up to and including, and not including 0 and 5. Right, and so remember, the open interval does not include the endpoints. Okay. So if this is the interval that we're talking about, so between 0 and 5, not including those endpoints, then the sample space is also 0 to 5, right? Because those are all the possible outcomes from our experiment. And so the sample space which I'll try to make a kind of a script C here, is the open interval from 0 to 5. Okay. What we're going to do is I'm going to let A be the open interval from 1 to 3. B can be the open interval from 2 to 4. And C is the half closed, half open interval. So it's closed on 3, but open on 4.5. So we can have a combination of these two. And of course, the square bracket, I don't think I mentioned it, but I am assuming that you're sort of familiar. These square brackets mean including those endpoints. So up to and including 0 to 5, right? In this case, it includes 3, but not up to, but not including 4.5. So when we're talking about number lines, the easiest way that I find is to visualize it using a number line. Okay, and so, we can visualize the sets using a number line. All right. So what I like to do is I like to have first the number line down below, and then I like to draw out each set above it. Okay, and so I leave a little bit of space here and I draw just my number line, right, from showing from negative infinity to infinity. The region that I'm interested in is just the sample set, right? So 0 to 5. So what I'm going to do here is I'm going to mark off 0 and 5 and just kind of show that I'm zoomed in on 0 to 5. And then I have 1, 2, 3, 4. Got a little spacey, but that's okay. All right. So it's just to help us figure out where they overlap, right, and where they don't. All right, so maybe what I'll do is I'll use different colors here. So A, I'll do in orange. Orange, be glad I didn't say banana. So A, I'll put on this line here. And so what I'm going to do is I'm going to draw A, okay, from 1 to 3, not including those points. So how we draw it to show that these are open intervals is we draw open circles from 1 to 3, and then I connect those with the line. I guess what I should do is I should start off by showing the sample space. I feel like I kind of did, but let's just illustrate it by an open circle, open circle. All right, so that's our sample space, but I kind of assume that, but there it is. All right, so now if I look at B, B is going to go on this line, so from 2 to 4, so an open dot at 2 and an open dot at 4, and join those two up. And then for C, closed point at 3, right? So from here, 3, right? Notice that closed point, that means including 3, up to 4.5. So 4.5, but not including 4.5. I'll put between 4 and 5. Seems reasonable enough, right? Okay, so now that we have these number lines, it's easier to see where there's overlap and where there's none, right? And so remember that these open circles mean that there's nothing there, right? It goes very, 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 very close, infinitely close, but it doesn't actually get there. Okay, so in terms of this point at 3, right? 3 is in C, but it's not in A. 3 is also in B, right? All right, so now let's use this number line to see what we can get here. So what if I ask you to find A or B? So anything that's in A or B. Well, if I look here, it has to be in A or it has to be in B. Now there's a bit of overlap here. So even though this endpoint at 2 is not in B, it is in A, so it's covered there. So what I'm going to do is I'm going to go from 1, but not including 1, all the way up to 4, but not including 4. Right, so an open interval from 1 to 4. Okay. What if I want to talk about A and B? Okay, so now I'm looking at just the overlap between A and B. So where that is, right, is here, starting at 2, but not including 2, and then going up to 3, but not including 3. So that's going to look like this, 2 to 3. Okay, what about B and C? B and C. So C starts here at 3, including 3. So that's where we're going to start our overlap. And then it ends here at 4, not including 4. Okay, so how we show that is it started at 3, including 3. So we have to use nice square brackets up to 4, but not including 4. What about something a little bit trickier, right? What about A and B or C? Okay. I don't have B or C yet, so I'm going to start there because it's in brackets, right? I'm going to start inside those brackets, and then I'm going to look at the intersection with A. And if you find it useful, you could map another line here with B or C, but first I'm going to start with A and B or C is what? So it can be in B. So starting here at 2, not including 2, or jumping up to C when I get there because I see that it extends a little bit further, or 4.5. So it's an open interval from 2 to 4.5. Okay. So you could, like I said, you could draw another line here to denote B or C, right? From 2 to 4.5. And if you find it useful, I'll do it temporarily here. Let's see if I can find a color, a temporary color, purple, right? And so B or C looks like this. So it starts at 2 and then it goes to 4.5, right? If you find that useful, I am going to remove that one, or maybe not. Maybe I'll just keep it. I guess there's no harm. Just wanted to keep it a little bit cleaner, but that's okay. So whether you want to fill in A is from the open interval from 1 to 3, or if you find that it's easier, I definitely find it's easier to just look at the overlap, right? And so what I'm going to do is I'm going to scoot this over and just fill in A. A is the open interval from 1 to 3, right? Yeah. Okay. So we could do it this way, or let's just look at the overlap, right? Because we want to find A and B or C, right? So the overlap starts here at 2 and it ends at 3. Open interval from 2 to 3. Okay. What if we want to find something even trickier, like A and B, or A and C? From earlier, I know A and B is the interval from 2 to 3. Right? How about A and C? Do I have it yet? I do not. So I have to find it. Okay. And so how I'm going to write this is I have A and B from before, and that's 2 to 3. Union or A and C. A and C looks like there is no overlap, right? Because A goes from 1, not including 1, up to 3, not including 3. But then C picks up just at 3. But remember, A only went up to not including 3, and then C picks up at 3 and goes until 4.5, not including 4.5. So the overlap here would be the empty set, right? It's still a set, and we can do that, right? The interval from 2 to 3 or the empty set, it can be either one of those. So that means it's going to be 2 to 3. Again, notice that these two are the same, right? These intervals are the same. And again, not a fluke, right? And we'll talk about the distributive laws next. Okay. In fact, right now, I guess. So here, let me see, do it in green. the last two examples illustrate the general distributive laws. Okay. And the general and I only need one more line, I think. So I'm gonna just bump this up one more sheet, just a little bit, like that. Okay. For any sets A, B, C, notice that's just a C, not the samples. Yeah, not the sample space. What we're gonna have, the general distributive laws say that A and then brackets B or C, if you have to distribute this A and into the brackets, right? That's what we're doing when we're distributing, is distributing into the brackets, or basically breaking up those brackets, expanding those brackets. We get A and B, right? So the A and attaches to the B, but in brackets, or, and then the A and attaches to the C, and that's how we distribute it. A and C. Okay, good. So that's what the intersection or and. So with the union, it works similarly, right? So we have A or B and C. Notice that these are opposites symbols, right? So it goes from and to or and we're distributing. So it only works for these two cases. But it works the same for both. So A or B and A or C. Okay. Let's just confirm this first line with a Venn diagram. The two Venn diagrams are going to end up looking the same. So if you're not following along, it's not going to look very useful, right? But I encourage you to try to draw out both sides independently in Venn diagrams, just to see how the same area comes about. So what we're going to do, we will confirm the first distributive law using Venn diagrams. So if we're going to try to draw A and B or C, it's really important that we draw B or C first, right? Because it's in brackets. But I'll also write out the right-hand side, A and B, or A and C. Okay. All right. Oh, I guess this is our first time that we see 3 sets in a Venn diagram. What's really important is that you want to have all 3 sets sharing some overlap, right? And this is just to visualize things. There are cases where there is no overlap between 2 of them, but then you just wouldn't shade it in, right? And so just in general, for 3 sets, we're going to draw them like this. So we draw our sample space, maybe a little bit bigger. A, B, and C. I'll label them like that. And then because I can, I'm just going to cheat and copy this over here. Okay, so on this one, I'm going to draw A and B or C. And here I'm going to draw on the right-hand side, I'm going to draw A and B or A and C. Okay. There's going to be multiple layers here. And so where I want to start is B or C, okay? Which means that, how can I start this? It can be in B. So I fill in the entire B circle, or it can be in C. Okay, so that's this blue area. Okay. If it has to be in A as well, right? So now I have the blue area and I will want to look at A and that blue area. So it has to be in the A circle and the blue area, which is only going to be these three regions, right? These tiny three regions. And so here, I'm just going to shade those in. Okay. And so this pink region is the entire thing. But like I said, it's going to be hard to see if you just look at the notes, but hopefully that works out. I don't know. We'll see. Now let's look at the region of A and B. Okay, so A and B, let's see here, A and B. So here I've got A, here I've got B. The shared region between the two is going to be this overlapping region, right? Because it has to be in A and it has to be in B. Oh, maybe I shouldn't do it so hard because this is our first one, right? And so notice that it does include this little triple intersection, right? So that's this one, A and B. How about A and C if I switch colors here? A and C. So it has to be in the A circle and in the C circle, right? And so the only way that that happens here is like that. Okay. So now when I look at the or, right, that's the green region or the orange region, which is the same as the pink region over here. So instead of coloring it over, because then it'll just go over all the colors I just put there. So instead, I'll just put pink around it. Right? But in theory, we could just shade this all in pink because that is the area that we want, right? And notice that the two areas are the same, and so these two statements are the same. Good. Same thing, you could do the same thing, whoops, you could do the same thing for the second statement, but we'll leave it at that. Okay, good. Next, we have De Morgan's laws. De Morgan's laws deals with the complement. Okay, so De Morgan's laws says, and I'll highlight that because that's going to be important, for any sets A and B, De Morgan's laws, notice that it's plural, it's because there are two of them, says that A and B, notice that that's in brackets, the complement of that, the complement of A and B is going to be the complement of A or the complement of B. So here I'm distributing this complement, right? I'm distributing the complement onto the A, that's fine. But when I distribute the complement onto the intersection, it somehow becomes a union. And of course, there's proofs to back that up. But for us, we just need to memorize that. It's the Morgan's laws, and so we're allowed to just use them, right? So, but you could look up the proof if you want to. But so when you distribute the complement, right, onto A and B, it becomes the complement of A or the complement of B. How about the next one? A or B, the complement of that. I think you can take a guess at what it's going to be, right? It's going to be the complement of A, okay. And again, it switches the sign to the intersection. So, and the complement of B. So again, we can verify these with a Venn diagram. So let's do it. We can verify these with a Venn diagram. Okay. Let's see here. So I've got A and B, and I'm just going to do the first one is equal to the complement of A or the complement of B. I have a feeling this one's going to get a little bit messier than the one before, but that's okay. So I only have two sets in this case, A and B. And again, I'm just going to cheat a little bit and copy, put it over here. Okay. So what we want to do is we want to find the set A and B and then take the complement of that. Let me just pause here. Okay, so we're going to want to shade in the area for A and B temporarily, right? Because then we want to take the complement. So if you don't need to do that, then that's fine, right? But I'm going to do it and then undo it. You'll see what I mean here. So A and B is this area, right? Which means that, okay, if I want to talk about the complement of A and B, well, that's going to be everything outside that area. And so here, everything outside that area is not just restricted to A or B, right? It can be anything in the sample space. And so it can be any value as long as it's not in that intersection. Okay. So basically what happens is we end up removing this little intersection here. And sometimes what I like to do is I like to highlight it by just tracing along the outsides. Okay, good. So how about if I want the complement of A, right? The complement of A is everything outside of A. So whether that's in B or not, right? That's all the complement of A. So if I start there, say the complement of A, well, the complement of A is kind of everything outside of A. Yeah. What about the complement of B? The complement of B is everything outside of B. So now I just have to avoid the B circle, which means I'm going to try to go like this, which is always a little bit harder. I don't know why. but so everything that's not in B. So if it can be in either orange or blue, right, the only area that wasn't shaded was this middle area, right, this overlapping area. And so that's the area that we extract, right? But notice that if we wanted to, we could, wait, undo. We could go like this, right? And they would look the same. I'm going to keep those green lines there just because I find them useful, right? But really, this becomes, I'm going to copy and paste, put it down here like that, right? And so here it becomes this, and this looks the same, right? And so we can extend unions and intersections beyond just two sets. We can expand them to an infinite number of sets or n sets if we want to. And so how do we denote that? We denote it. I'll start fresh on a new page here, I think. We can extend unions and intersections to more than two sets. For example, if we have A1 union A2 union union A subscript n, right? Now I'm just using A's, A with subscript to denote different sets instead of A, B, C, D, E, F, G, right? I can have A1, A2, A3, A4 up to AN, just making room for n sets, okay? And so they're all joined with unions here, is what that's saying. And so what that set is going to look like is that's going to be the set of elements X, so a generic element X, such that X is an element of the set A subscript I for I equal to 1, 2, up to n. Okay. We could also write that as a capital U, so just a big union from I equals 1 to n of A subscript I. So it's just saying, okay, take the union of all the A's from A1 up to AN, right? And so take and collect all those unions. Or we could also talk about, I'll say versus the intersection. And I don't know the term when we have more than two sets that we're intersecting. I don't know the term, but it's got to have some term from. So the intersections of A subscript I, so A1 through AN is going to be the same, right? A1 and A2 and up to and AN. So that's just a heads up that we could look at more than two sets for a union or an intersection, and that's how we would denote them, right? But it's also getting us into the swing of things with I, right? Subscript I to denote a range of values, right? From 1 to n. Okay. How about an example? Suppose the sample space is the set 1, 2, 3, going on and on and on and on. Right? What can we call that? How can we summarize that verbally? Well, that's the set of positive integers. It looks like to me, right? And then we're going to say that if a subscript n is the set from 1, 3 up to 2n minus 1. 2n minus 1 makes an odd number, right? Because we're taking any integer n, right? And that's going to come up later, but I'm telling you n is an integer. So 1, 2, 3, 4, 5, 6, and it's a positive integer. So then if I multiply 2 times 1, well, I get 2 minus 1 puts me at 1, right? 2 times 2 is 4, minus 1 is 3. 2 times 3 is 6, minus 1 is 5, right? And so that's how we develop odd numbers in general. Okay. So if that's A, and then we're going to let B subscript n be n plus 1 all the way as far as it wants to go, right, to infinity. For n equal to 1, 2, 3, da, da, da. Then what we want to do is we want to figure out things like, okay, what if I have a union from n equals 1 to infinity of a subscript n? What's that going to look like? Remembering that the union is or, right? And so it can either be an A1 or A2 or A3 or A4. And as long as it's in one of those, it's going to be in the set. Okay. And so I always find it helpful to map out a few of these, right? So A1, maybe off to the side here, A1 is the set where n equals 1, right? And so it's going to go from 1 up to 2n minus 1, but 2 times 1 we said was 2, minus 1 makes 1, right? And so A1 is just the set 1. A2 is going to go from 1 up to 2 times 2, which is 4, minus 1, which is 3. So then 1 and 3. A3 is going to go from 1 to 2 times 3 minus 1, right? So 2 times 3 is 6, minus 1 is 5. So 1, 3, 5. Okay. A4 is going to be, just take a wild guess what it's going to be. 1, 3, 5, 7. Let's try it. 2 times 4 is 8, minus 1 is 7. All right, good. 1, 3, 5, 7. Good. So then we look at this pattern and it looks like it's just going to build up incrementally throughout all the odd numbers, right? So for each increment, we're going to add another odd number in the list, right? So this keeps going and going and going, right? And eventually we have the set of odd numbers. So if we take the union of all those, so it can be the set of A1 or A2 or A3 or A4, that's going to end up being just the largest possible version, right? Up to n equals, or n equals infinity. So that's going to technically go until infinity, right? And so this becomes the set of odd numbers, 1, 3, 5, keep going and going and going. Oops. That's a weird curly bracket. Close enough. Okay, so these can be a little bit tricky, right? But you just need to sit down and kind of map out the different scenarios, and then you'll start to see a pattern probably. Okay. What if we want to look at the intersection from n equals 1 to infinity of a subscript n? So now it has to be the overlap. Well, that one's a little bit easier, right? Because now I can tell that there's really only one value where there's overlap, and that's the starting point, right? 1. So it's just the set 1. What if we want to look at B? So the union from n equals 1 to infinity of B subscript n is what? Now it might be helpful to look at what B looks like, right? B1 is just 1. 1 plus 1 is 2. 3, 4, 5, 6, 7, 8, 9, 10, right? And so let's see if I can. So B1, actually, you know what? I'm going to scooch these around here because it might make more sense to have them in order. Order in the court. B1 is 1, 2, 3, all the way up to infinity. What's B2? B2 starts at 2 and then goes to 2 plus 1, 3, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? 2, 3, maybe I should go to 4. Right, and they're all going to go to infinity. How about 3? Well, if n is 3, then we start at 3 and then we go to 4 and then we go to 5. Keep going, right? And so on and so forth. So now we have a pretty good idea of what this looks like, right? And so if we're looking at the union of the B's, right? So the union from B1 to B infinity is going to be starting here at 1, because that is a possibility. And then if it's in B1 or B2 or B3, right, it's all going to go from 1 to infinity. So it's going to be the set from 1, 2, 3, and so on and so forth. Notice that that's also the sample space. So I'm going to make a note of that, which is the sample space. There, that's nicer. What about the intersection of all the B's? If we let n run to infinity, right? Let's have a look at what that looks like. So the intersection of n equals 1 to infinity of Bn is going to be B. starting at B1 and comparing it to B2, there's quite a bit of overlap here, right? Because the only one that's excluded is 1, and then it's all overlapping to infinity. But then we move to B3, right? And so now they're all overlapping except 1 and 2. So what's going to happen is for each B that we make, we're going to be excluding, we're going to chip away the first value, right? And if we let B run to infinity, then what's going to happen is we chip away all the front values until there are none left, right? In the intersection, in the overlap. And so what happens is this becomes the empty set. Right? So that's going to take some practice, right, to be able to see that. But it's good to have this under our belts at least, right? So we're not too scared, right? And so the key to solving these problems is going to be mapping out a few of these sets, right, and make sure that they follow the rules that are laid out here. So a subscript 1 is using n equals 1. A subscript 2 is using n equals 2, right? So on and so forth. And you loop through the n's. And then just being careful with considering the union or the intersection, right? The union, it can be in either situation, right? Either of the A's. The intersection, it has to be in both, right? Okay, so the textbook goes through and talks a lot about set functions, and it does involve integrals, which is Calc 2. Technically, I'm so rusty with my Calc layout, but I'm pretty sure it's Calc 4, potentially Calc 3, where we start doing double integrals, but don't quote me on that. Definitely Calc 2 though. And so that's hard for us to do because I don't think a lot of you have done Calc 2. So I'm gonna leave it and introduce whatever we need as we need it, but I'm not gonna do it now. So the last thing I want to do is talk about set functions. And you're probably familiar with functions, right? Functions take some input and return some output, right? And so recall a function takes some input and generates output, right? Just in general, depending on the function, right? That's going to depend, the output is going to depend on the function. Okay? So if we start with kind of an example, and I only really want to do an example for this one. If we let the sample space be the set of real numbers, and just to emphasize, the set of real numbers is the set from negative infinity to infinity, the interval from negative infinity to infinity, then for a subset A in the sample space, let Q of A be equal to the number of points in A that correspond to positive integers, right? Positive integers. I told you it's going to be so important to keep track of those. Positive integers are 1, 2, 3, 4, 5, 6, and nothing in between. Equal to the number of points in A that hey, what happened here? That correspond to positive integers. Okay. Then Q of A, oops, is a set function, of the set A. Okay. So what that means is it operates, or rather, I'll put it kind of down below here. It operates on the values in A. So if A is the set of x's such that x is between 0 and 5, not inclusive, what's Q of A? Well, remember, Q of A is going to be equal to the number of points in A that correspond to positive integers. So Q of A is going to return the number of positive integers between 0 and 5, not including 0 and 5. So then Q of A is, how many integers are there? Well, 1, 2, 3, 4. Those are the only ones that are in there, right? And so there are 4 integers in there, and I'll 4 integers, and they are 1, 2, 3, 4, just to highlight what they are. Because sometimes having 2 4s here might be confusing, right? But it's 4 integers. What if A is the set -2 and -1? I know that these are just the values, right? And each, so the -2 and the -1 are the elements, right? This is no longer an interval because an interval has to have round or square brackets, whereas these are curly brackets to indicate a set. So in a set of -2 and -1, there are no positive integers here, right? 1, they're both negative. They are integers, but they're negative, right? And so then Q of A is 0, right? 0 positive integers. I should say 4 positive integers, just to clarify. What if A is the set of x such that x is going from -infinity up to 6, but not including 6? Remember, we're talking about positive integers, right? And so from -infinity up till 0, there are no positive integers, there are only negative integers. And then starting at 0, right, we hit 1, 2, 3, 4, 5. 6 is not included, and so we have 5. So Q of A is 5, right? And so we have 5 positive integers. 1, 2, 3, 4, 5. All right. So that's good. That's where we're going to leave the set functions. And I think that's good for today. All right. So my apologies again, but hopefully this worked out too. All right. See ya.